If you were to shrink down to the size of a red blood cell, your experience of water would change entirely. At that microscopic scale, the physics of fluid dynamics shift. Water stops feeling like a free-flowing liquid and instead behaves like thick, heavy molasses. Every microscopic movement requires you to push through incredible resistance. Scaling down our traditional technology to this level runs into a hard physical limit. If you shrink a standard battery to the microscale, its capacity to hold a charge effectively vanishes. And if you try to use tiny mechanical gears, the sheer friction of this molasses-like environment would tear them apart. This forces a departure from how we traditionally build engines. We cannot simply make everyday machines smaller. To get mechanical parts moving at this scale, engineers have to find ways to pull energy from the surrounding environment itself. Mastering these forces is the prerequisite for any technology meant to operate within human anatomy. Solving the power dilemma allows a machine to physically intervene in biological processes at the cellular level, rather than merely floating passively within them. The thickness of the fluid is only half the problem. Microscopic objects are also subjected to Brownian motion, a constant chaotic bombardment by water molecules that relentlessly hit and spin the machine in every direction. In our world, you can glide after a push due to inertia. In the micro-world, inertia is effectively non-existent. The exact millisecond a motor stops applying forward thrust, the object stops dead in its tracks. So a viable micromachine faces a dual hurdle. It must extract continuous directional force from a sticky, chaotic environment, and it must do so without any external wires or tethers to supply the energy. One solution uses localized chemical reactions to generate thrust. Researchers have developed tiny, 3D printed rotors made from silk, a material that allows them to embed reactive agents directly into the structure. Placing catalase into specific nodes on the rotor's arms causes a reaction with hydrogen peroxide. The enzyme produces microscopic oxygen bubbles at those colored points. As these bubbles burst, they act as miniature thrusters, providing enough force to push the arm in the opposite direction. By converting the chemical fuel present in the liquid into physical movement, these silk structures can achieve continuous mechanical rotation. Scientists have successfully replaced the need for a battery with a localized chemical reaction. A second strategy avoids synthetic engines by hijacking living organisms, specifically E. coli bacteria, to serve as biological propellers. Scientists print microscopic circular stables with 45-degree ramps. Bacteria swim up and wedge into chambers, their free-whipping tails physically spinning the gear. Modified to respond to light, these biological switches only spin the motor when illuminated, letting researchers turn the engine on and off. This hybrid approach proves that living organisms can be successfully integrated into human-made machinery as highly controllable self-fueled engines. The final strategy involves synthetic molecules embedded in a soft polymer gel that act like microscopic ratchet wrenches. When a chemical fuel shape locks into the center of the ratchet, it forces the top half to rotate exactly 90 degrees clockwise. As millions of these ratchets spin simultaneously, they grab and twist the surrounding polymer strands together, much like winding up a rubber band. These photographs show the result. On the left is the original gel. On the right, after feeling, its physical volume has dramatically contracted. These molecular ratchets have accomplished the goal of translating invisible, nanoscale chemical reactions into measurable, macroscopic physical work. This technology has immediate practical uses in the lab. These circular diagnostic wells are often limited by how slowly chemicals diffuse through them. By placing bubble-powered rotors inside, they act as autonomous microstirrers, speeding up the detection of diseases. The ratchet gels are equally versatile. By feeding the contracted gel a mirrored version of its chemical fuel, the ratchets spin in reverse, allowing the gel to unwind and expand back to its original size. Despite these breakthroughs, a core limitation remains. None of these engines work in pure water. They all require specific, heavily controlled chemical or biological environments to function without stalling. Even with these limits, we have proven that we can transform static liquids into environments for active, programmable machines. This points toward a future where autonomous nanobots could navigate the human bloodstream. By drawing energy directly from the body's ambient chemistry, they could operate without the need for traditional batteries. We have finally found a way to work with the sticky, chaotic physics of the microscopic world, rather than fighting against it. By extracting order from molecular chaos, we have turned a passive environment into a functional, mechanical microworld.